Okay, I'm going to try to do this as fast as I can and skip a bunch of things that I know I'm going to talk about during class. So we're talking about non-renewable energy resources, and we already started looking a little bit at gasoline, oil at least. Um, so in addition to what you saw in that Alaska's Last Oil movie, we're also talking about other non-renewable fossil fuels like coal and natural gas. But non-renewable energy also includes nuclear energy because they're energy resources that can't be easily replenished within our human lifetimes. They may recycle, they may take thousands of years, millions of years in cases of fossil fuels, but that's not really renewable for us humans. So, coal, oil, natural gas, and nuclear energy. Finite amounts of resources. And you know what they do. So, non renewable energy resources, fossil fuels, coal, oil, natural gas, in that order. That's the order of how much we use them, in this country at least, and nuclear fuels. Fossil fuels come from biosources, so they were once millions of years ago living organisms and became fossilized. Thanks to those millions of years, sedimentation, being pressurized closer to the center of the earth. We burn those fuels, and those biological molecules, they have a lot of potential energy in their bonds, if you guys remember that kind of stuff. And I guess a key term you should know that's not written on here is combustion. So the chemical reaction of burning these organic compounds, coal, oil, natural gas, biomolecules, is called combustion. And one of the main products of the combustion reaction is carbon dioxide, CO2 gas. This gas, however, is for the major energy sources of the world. And so oil is the most used. And then coal. Repeat is kind of a lower form of coal, less energy efficient form of coal. That's a better word. Then you have natural gas. We're starting to use renewable energy a little bit more. Maybe that number has changed since this book was published in 2012. And then nuclear fuels, 6%. And then make sure you write down somewhere on your notes how are nuclear and fossil fuels different. So energy use, it's not evenly distributed throughout the world. For example, the U.S., in your book, it tells you the stat that the U.S. used 5 times more oil, or more energy, than the rest of the world average in 2007. I had to look at my notes for that because I couldn't remember it. So it shouldn't be too surprising that developed nations and people in developed nations that make up 20% of the whole population, I think is the number, use 70% of the world's energy each year. And these are the ones that we tend to use in developed countries. Commercial energy sources, those that are bought and sold, coal, oil, natural gas, we buy and sell them, developed nations. But in developing nations, people still may rely on subsistence energy sources, things that are gathered, resources that are gathered by individuals for their own use, for their home use, for cooking, such as wood, charcoal, and animal waste. So here you have some charcoal. Remember that in Haiti, charcoal is a big, huge deal. Developing nation, subsistence energy source. I can't remember why this slide is on there. Natural capital. Natural capital basically is just another word for valuable earth resources. So those that provide us humans with goods and services. We have, of course, water. We have oil, natural gas. We have all these big, valuable ones. Coal, mine coal, geothermal energy. But it's also other natural valuable resources, such as arable land, areas for recreation, even things like biodiversity, and those kinds of natural capital, those kinds of valuable earth resources came up in the very, very beginning of the semester. I want to say chapter 3. It was called, or it was further categorized into provisions, regulating and supporting services, fancy UN terms like that. So the process of energy use, meaning from the energy resource to you turn on your TV, I think is this thing right here. So first you have to find your energy resource. You have to extract it. The machines that you use to extract are going to use fuel, of course. You're going to transport it. You're using fuel. You're losing energy as heat. That's what these arrows, red arrows are. You transport it to a processing plant where they process it, they purify it, they distill it, whatever they have to do, clean it up a little bit, until they finally combust it. So combustion, energy conversion. They're burning it in this case. I don't know if you can tell if there's fire. And then in this case, you're generating electricity. So I'm assuming that this is coal. Yeah, looks like coal. Something has to transport the waste away, but the energy that is being produced by this generator goes through your transmission wires and finally gets to you. You turn on your TV. Okay, so lots of steps in the process of energy use. Just numbers, just so you kind of know that the energy of converting coal to electricity, so we're looking at this part right here. So all that coal that's being burned, combusted, to generate electricity, this process is actually only about 35% efficient. If you remember when we're talking about energy efficiency, 35% efficient, changing it from, potential energy bonds in coal to generate electricity. And that's not taking into account absolutely all these other steps. So we are losing energy in all of these steps from the original resource to you. And the energy return on energy investment, long term, is equal to the energy obtained from the fuel divided by the energy invested to obtain the fuel. So, and really quickly, just kind of remember in the back of your head that we're talking about, or we're relating this energy loss, this energy efficiency, loss of energy from one energy step to another, to the law of thermodynamics that says that as you're converting energy from one form to another, you're losing a lot as heat. So the overall fuel efficiency of U.S. automobiles has been getting better as the years, they were much less efficient in the 75 at least than they are now. And this doesn't even show hybrids and electric cars that have some decent mileage. It's at least improving is the point of this slide. And electricity generation, we'll look at this again in class. There's a live animation that will show you. And right here, we're looking at coal as the energy source, but we generate electricity pretty much the same way. These steps are pretty much all the same. The only difference is probably going to be just which energy source we start off with. Okay, so whatever the fuel is, it's going to be burned or heated or somehow assisting the process of boiling water. In this case, you have coal. You're pulverizing it. You're making it to super fine powder. You're increasing the surface area. You're burning it. And the burning thing, the combustion, the heat released from this combustion reaction is used to boil water to turn it into steam. And the steam moves along this pipe. The steam turns a turbine, which is kind of like a bunch of, think of a bunch of high-tech pinwheels. Oh, here you have a nice turbine. Pretty. Turbine's connected to a generator. The generator spins. Probably it's got some incredibly awesome magnets in there. As it spins, it generates electricity. The electricity runs through your transmission lines. And the water, which was steam over here, it's still passing through this whole system. The point of this water is it has to keep going through these tubes and get cooled, so it gets condensed, and it could be reused once it's nice and cooled and condensed, and this process can keep going. But a lot of times they just actually they may cool this water and spill it out into the environment, and that may be a problem if it's not cooled. It may enter a lake and heat up a lake. And what's going to happen when you heat up a lake where you have fish that are used to a certain temperature? Suddenly you make it warmer. So that could be a potential problem, or it has been in the past in some places. So that's cool. If this were a nuclear power plant, we would be using, instead of coal burning, we would just be connecting this to a nuclear reactor that would get so hot that it would convert this water to steam. And the nuclear fuel source would probably be uranium. And electricity generation. So no matter what your original fuel source is, the primary fuel source is whatever is eventually whatever's being burned to make electricity. The burn fuel from the coal transfers energy to the water and becomes steam. Kinetic energy contained within the steam transferred to the blades of the turbine. Device that resembles a fan. As the energy in the steam turns the turbine, the shaft in the center of the turbine turns the generator. The generator generates electricity. That's what this is all trying to tell you. Most coal burning power plants are about 35% efficient. This is a number that comes up a lot, so make sure you know that. Coal generating electricity, there you go, is about 35% efficient. If you look at this chart, look at the different fuels that we use in the U.S. It still hasn't really changed. We use mostly coal. The reason we use coal the most is because we have a lot of coal in this country. We also use some oil. We also use some natural gas. We also use some nuclear fuels. I bet this number has gone down more recently. Don't quote me on that. I'll check it. Hydroelectric dams, other sources of energy. Okay, mostly coal. Cogeneration. Let's see what I wanted to say about cogeneration. Cogeneration just means that you are using a fuel, you're burning some fuel to make electricity, but you're also using that fuel or the heat that's released from the combustion reaction, for example, to heat up a place, to produce heat, to warm up a building, for example, for heating purposes. For example, if steam is used for an industrial purpose or to heat buildings, it is diverted to turn a turbine first. And, they mean and. This improves the efficiency to as high as 90%. Okay? We're gonna do a chart that's comparing the origins of coal, like what the bio origins are, what the primary origin for coal is, for oil, for gas, and the advantages and disadvantages of them. So make sure that you read through them in your book, and definitely note them down, write them down, and have them as kind of a little study sheet. But very quickly, coal is a solid fuel, basically. Think of big charcoal briquettes formed primarily from the remains of trees, ferns, and other plant materials preserved 280 to 360 million years ago. Ferns is probably the one that's the most popular. popularly known, excuse me. It was probably the most abundant. Ferns. Big plant matter is coal, which hopefully doesn't surprise you too much because, think of coal and big bark. Fern forests of the Carboniferous era. Coal is ranked from lesser to greater age, exposure to pressure, and energy content. So coal can be more efficient or less efficient. Just kind of depends on how much water is in it, how much pressure, how pressurized it was, and age. The longer the coal is made, basically, the more it's going to be under pressure, exposed to pressure, and the more energy content it's going to have. 4 types are lignite, bituminous, and anthracite. And the largest coal reserves are in the U.S., Russia, China, and India. And of course, the U.S. big. We have lots of charcoal. Do know this. This we may actually get a chance to do a little lab on it. Coal, plant matter, plant fossil fuels. This is a picture of how coal is made. You guys can check that out on your own. Advantages and disadvantages of coal. Make sure you know these. I will talk about them some more in class. Is there anything that is not in here that I kind of want to be in there? Coal is 60 to 80% carbon. Anything else? It's got lots of extra things in it, lots of impurities in it. Don't forget that we mine for coal. We may do subsurface mining. Excuse me, I meant to say surface mining, so shallow. That might be open pit, might be strip mining, might be mountaintop removal mining, but we might also do subsurface mining. Just kind of a review. Don't remember what this was, but it's some sort of mudslide as probably a result of some sort of open pit or mountaintop removal. Petroleum, liquid fuel, oil, mixture of hydrocarbons, so carbon and hydrogen, a little bit of water, some sulfur, in underground deposits. Because it's a liquid, it's ideal for putting it into your moving machinery, so your cars. And it comes from ocean-dwelling phytoplankton. So think of petroleum in the oceans thanks to your phytoplankton that died 50 to 150 million years ago when most of the earth was actually warm and lots of phytoplankton producing. Countries with the most petroleum: Saudi Arabia, Russia, the US, Iran, China, Canada, and Mexico. And sometimes I see a question like this every once in a while on an AP exam. And I'll show you how oil is formed in video. Picture of petroleum. Petroleum you have to mine to get to the oil that's locked underneath an impermeable rock. And whenever you have an oil deposit, you often have natural gas there as well. Let me see. What else did I want to say? Nope, that's it. A little bit of science on what we do with oil. So we might drill for oil, but we may distill it. So as a liquid, you can distill oil and collect various different types of oils at different boiling points. They're all going to have different boiling points. This is how we separate these different components of crude oil. And from this distillation process, we might get some oils that we use for asphalt. So for our asphalt, for grease wax, for some solvents, for some diesel oil, for heating oil, aviation fuel, gasoline gases. Okay, lots of different more purified oils within our crude oil. Here's a kind of nice picture of a refinery. We'll talk about advantages and disadvantages of petroleum in class. We'll also talk about advantages and disadvantages of natural gas, but I'll talk about it really quickly. Natural gas exists as a component of petroleum in the ground, as well as in some gas deposits that are separate from petroleum, but very often together with petroleum. It's actually 80 to 95% methane, 5 to 20% ethane, propane, and butane. And because it's actually 80 to 90% methane, methane is CH4. I should have written that down somewhere. It makes it slightly more efficient to burn, a little cleaner. You don't have all these other impurities that your coal for sure definitely has. But because you're combusting methane, you're still releasing a lot of carbon dioxide. We'll talk about this part. In terms of things that you might know about natural gas or methane, we tend to use it in our heaters. Other fossil fuels, often they're just harder to get. Maybe they're just more expensive to get. Maybe it's harder to get them and refine them better. So oil sands, you may have heard of oil sands. Slow-flowing, thick deposits of bitumen mixed with sand, water, and clay. And bitumen, which you may know as tar or pitch, is a more degraded type of petroleum, where your bacteria have chemically metabolized some of the lighter hydrocarbons, and others evaporate. We'll talk a little bit about fracking too, because I kind of just like it, or not like it. I like talking about it. It's an interesting topic. That's what I meant to say. It's controversial technique, and we'll look at that in a second. So the Hubert curve. This man, Hubert, M. King Hubert, said that we're going to run out of oil at some time. We're going to use up all our resources of oil and run out of it. The curve is the graph that shows the point at which world oil production would reach a maximum and the point at which we would run out of oil. So this is the maximum oil production. So basically this is how much oil we have produced. And once we hit that peak production, we're going to start to use it up. He had originally given an estimate that, I'll come back to this because I don't have the numbers written down, of when he thought we would just run out of oil. We've found some more oil fields since then, so we've prolonged it a little bit, but I mean, we're still going to run out of them. We're just using them like crazy. Oil is probably the most quickly depleted oil. So the future of fossil fuel use, even though we're using energy more efficiently, even though our cars use oil more efficiently, even though we're starting to develop some new energy technologies, our population is increasing. We're using more energy per person. We're increasing our standard of living, so we're using more energy per person anyway. So we need to start shifting our focus on how to make renewable energy resources, right? We kind of just have to. So if current global use continues, we'll run out of conventional oil in less than 40 years. Coal supplies might last for another 200 years, maybe much longer, but it's still a finite amount. It's still going to run out, and our population is huge, and we use a lot of stuff. Talked about nuclear energy. Should I go through it? Also, non-renewable, because I only have a limited amount of nuclear atoms, basically. So in nuclear energy, we're usually talking about a uranium-235 sample, nucleus in this case. They're looking at one at a time here. We force it to undergo a reaction by hitting it with the neutron, hitting the nucleus with the neutron, and it forces it to undergo fission splits, and it splits into two different atoms than whatever it originally was, the uranium-235. When this happens, when it splits into two, when fission occurs, there's a huge amount of energy that's released. Okay, this is an incredibly reactive, high energy process, releases lots of energy. And so if you think about your electricity generation, small amounts of uranium-235 are going to release so much energy and heat up a lot of water. Okay? Then we do that to a whole bunch of uranium nuclei and release lots of energy. Nuclear reactors, nuclear power plants, basically a lot like coal power plants, but the fuel that we use is not coal, it's uranium. We might put some uranium in these where is my core? Sorry, my core. Fission occurs there. Water turns to steam. Steam turns a turbine. Turbine turns a generator. Generator generates electricity. Goes through our power lines. Pretty much same thing happens. Just maybe a little more dramatically. So our water is probably steamed up a little more intensively. And we have to put all these control rods to and soak everything in water to cool everything down, because there's so much energy released that we want to make sure that this whole operation doesn't just melt. Literally melt. The meltdown really literally means melts everything here. So fuel rods are those tubes that house nuclear fuel. Nuclear power plants work by using the heat from nuclear fission to heat the water. The water produces steam, turns a turbine, turns a generator, generates electricity, goes through all your electric wires. Control rods are devices that can be inserted between the fuel rods to absorb excess neutrons, thus slowing or stopping the fission reaction. So you can go back and look at all those pictures. Advantages and disadvantages, put those into your charts. We've already calculated half-lives. We might review them. And maybe one of the biggest scary things that people think of when they're talking about nuclear power plants is what happens if there's an uncontrolled meltdown. Well, I will tell you that it hasn't happened without there being like some person who just didn't pay attention to the temperatures of the plant. So basically, the risks for it happening are really low, but it has occurred, and it does tend to be very intense. And I'll show you a video on that too. Are we done? We talked about radioactive waste. We saw it in the Bill Nye video. We will do that in class. And radioactive waste is probably the biggest thing to deal with when we're talking about how to create electricity from nuclear energy. Fusion, as opposed to fission, is the reaction that powers the sun and other stars. So it happens in the sun and in the stars. Fusion means to fuse, and it occurs when you have lighter let's start with a lighter nucleus that's forced with another nucleus, and they produce is a better word, a heavier nuclei. Heat is released, lots of heat is released, super lots of heat is released. That sun that we have, all that nice heat is thanks to fusion. Nothing's combusting in there. There's no burning per se. It's all fusion. Fusion's a promising, unlimited source of energy in the future, but so far we haven't been able to really do it. Containing, not containing. And hopefully that wasn't too incredibly horrible. And if it is, I'm actually going to cut it down.